Hey guys, Mrs. Hijic here with your Change in Motion Objective 3 video. Make sure you have taken a moment to set up your Wix. Our objective today is to know how energy is stored and how energy affects work. And there are 8 essential questions for you to answer, along with a support item, which I will show you at the end. So pause your video now and get your Wix set up, and then we are ready to go. Let's first start by defining the word energy. The scientific definition of this word is the ability to cause change within a system. And a system can really be anything that you want it to be. The system can be the human body. And of course, it takes energy for the human body to change its position, to change its motion. It also takes energy for the human body to gain weight and lose weight. And so anything that requires a change to a system, that change is caused by energy. And we measure energy in a unit known as the joule. Energy is required for us to do work, which we will talk a little bit more about work towards the end of this presentation. Are there different types of energy? Well, the answer is no. Energy is simply energy. We can see it in different forms, but there are really no different types of energy. There is, however, 2 different ways that energy can be stored, and we call this energy storage. And so the 2 ways that energy can be stored are as potential energy and kinetic energy. Now, potential energy storage is energy stored within the position of an object, whereas kinetic energy storage is the energy that is stored within the motion of an object. And we'll see how energy can be transformed from one type of storage into another and back again, but there are really only 2 ways for energy to be stored, and that is through kinetic and potential energy. Let's look at some examples of potential energy first. Again, this is energy stored in the position of an object, like a gravitational potential energy, which is energy stored within the position of an object and its height above the ground. And so a couple of factors determine the amount of GPE, or gravitational potential energy. That is the height of the object, the mass of the object, and also the amount of gravity. As the height increases, so does the GPE. As the mass of the object increases, so does the GPE. And as gravity increases, so does the GPE. Now here on Earth, gravity is pretty set at 9.8 newtons. That is the force of gravity on the Earth. But if we were able to move to another planet like Jupiter, which has a greater gravitational pull, or the Moon, which has a lesser gravitational pull, then our GPE may be different according to the differences in gravity. But here on Earth, gravity is standard. It doesn't change. 9.8 newtons is our measurement for Earth's gravity. Then we have elastic potential energy, or EPE, and this is the energy that is stored in the bending, stretching, bouncing, or twisting of an object. So when you have a rubber ball and you bounce it, or a basketball and you're bouncing it down the court, every time that ball strikes the ground, there's some energy stored in that sort of compression of the ball as it hits the ground as EPE, or elastic potential energy. Magnetic potential energy is also a form of potential energy. This is energy stored within the magnetic fields. Now, magnetic fields are invisible. We can't see them, but we can feel them as the attraction and repulsion, like you would with magnets. You can't see the force of magnetism, but you can feel it. And so based on the position of a magnetic field, that is also an example of potential energy. Electrostatic potential energy is also a form of potential energy, and this type of energy is formed when friction causes electrons to jump around from one object to another, and when an object becomes electrostatically charged, you can see the repulsion. For example, this little kid's hair is going all crazy because he has an electrostatic charge built up. Electrons have built up in his hair, and each strand is now repelling one another because they are like charged. They're all negatively charged. And so you can see he's got crazy hair because each hair strand is pushing away from another one as a result of this electrostatic PE. So the position of the electrons causes this type of potential energy. And then we have chemical potential energy, which is energy stored within the chemical bonds of a substance. Food is a great example of chemical potential energy. When we digest food, our digestive system breaks down these bonds, and the energy stored within those bonds is then used by the human body to do things, to go out and run and play basketball and volleyball and soccer and all those fun things. It helps us think and do our homework and watch our Wix. Another example are batteries. Batteries are great examples of chemical potential energy. There's energy stored within the battery. That chemical energy is converted into electrical energy when the battery is plugged into an electrical device like your cell phone. And then lastly, we have nuclear potential energy, which is energy stored within the nucleus of an atom. And anytime the nucleus gets changed in any way, this nuclear energy is released. And so some examples now of kinetic energy. Remember, this is the type of energy storage that has to do with the motion of an object. So here, these examples are not going to be based on the position of anything, but on the motion of these objects. The first example is mechanical energy, which is the energy of motion, which is attributed to a specific object. So both the boy and the bike in this picture have mechanical energy because they are in the process of moving. Thermokinetic energy is also called heat energy. This is the total energy that's contained within the particles of a substance. All atoms that make up all material are constantly moving, and the amount of movement determines their temperature or their thermal energy. More movement, more thermal energy. Less movement, less thermal energy. And so this has to do with the movement of atoms, of all the particles that make up a substance. And then we have electrical kinetic energy, which is the energy associated with the movement of electrical charges or electrical current. We know from our study of the atom that protons and neutrons are in the nucleus where they're kind of stuck like a vault where they can't escape. But the electrons in the electron cloud, they do have the ability to move from one atom to another. And so when an atom gets charged, these electrons have the ability to jump from one atom to another. And this movement of electrons through a substance is electricity. And so we get this electrical kinetic energy with the movement of electrons. Sound energy is also energy of movement. This occurs when energy is transmitted through a medium or through matter, through vibrations. And so anytime something vibrates, those vibrations are transferring sound energy. Electromagnetic kinetic energy, which is also called light. We've studied already when we were studying our electromagnetic spectrum unit. And so electromagnetic energy is simply energy that travels in waves, and that can travel through a vacuum, which is why electromagnetic radiation is the only form of energy that can travel through light. And so remember, we have radio, microwave, infrared, visible, ultraviolet, X-ray, gamma, some of which are ionizing, some of which are non-ionizing, but all of these forms of energy are electromagnetic kinetic energy because all of these forms of EMS or EM radiation move. Now, we do have, energy has the ability to be transformed from one form into another, starting with potential energy and transforming into kinetic energy. And one example of that is a roller coaster. Now, over here on the right-hand side, we have these bars, which represent the amount of kinetic energy, potential energy, and then the total amount of energy within the system. And so this roller coaster is a closed system where there is no friction. If there was friction, we would have another bar over here for thermal energy, but we don't, so this is a closed system. Now notice when the roller coaster starts up here, all of the energy is stored as potential, more specifically gravitational potential. And as the position and movement of the cart changes, so does the amount of PE and KE. As the cart goes down the ramp, the amount of gravitational potential energy is decreasing because the height is decreasing. And as this cart rolls down the ramp, its speed is increasing, so its KE is going up. So at the bottom of the roller coaster, our GPE is at its lowest point and our KE is at its highest. And when the roller coaster goes back up like a loop-de-loop or one of the hills, the GPE goes back up because its height is increasing and its KE is going down because its speed is decreasing. So we can see that we have a transformation of energy from one form, PE, into another form, KE, but the total amount of energy within our system is staying constant because this is a closed system with no friction. Here is another example of a potential energy kinetic energy transformation. Here we have our kinetic energy, our GPE, our EPE, or our elastic potential energy, and then our sigma E, total energy within the system bar. And so you can see that when this bungee cord is stretched, its elastic potential energy is at its greatest. So we have that gray bar that's all the way very, very big. And when the weight is at its highest position, its GPE is the greatest because it's at the highest point above the ground. And then as soon as that bungee yanks on that blue weight, the movement is going to be at its fastest, and so our kinetic energy is highest right about here when that bungee cord pulls, and then the weight is constantly changing speed throughout its bounce. Here again, this is a closed system with no air resistance or no friction. If there was friction, we would have an additional bar again with thermal, and what would happen is that the total energy of the system would begin to go down. It would dissipate as that energy would be transforming into thermal energy, which can't be used again by the system, and eventually the bungee cord would stop moving because there would no longer be any energy because all of the energy within the system got converted into thermal energy as a result of friction. So I told you earlier that we would come back to work, and here we are. So work does take energy. The definition of work is that work is done when a force is applied to an object and that object moves in the same direction as the applied force. So there are two factors that determine work. The first factor is force. How much force is applied? Okay, the more force you have to apply, generally the more work you're going to have to do. And then also the distance that the object moves, because you have to apply a force and you have to move an object, and how far that object moves is going to also determine the amount of work done. So more force applied, more distance moved, more work is going to be done. So those are the two factors that determine the amount of work done. Again, that is the amount of force applied and the distance that the object moves. Now the key to work is that the object has to move in the same direction as the applied force. So let's try and determine when work is being done. If I apply a force upward and the object moves a distance that is upward, is work being done? I hope you said yes, work is being done, because the direction of the applied force and the direction of the distance that the object moves are the same. What if I applied a force up on an object and that object moved forward a distance? Is work being done? Well, I hope you said no work is being done. Work is not being done in this case because the direction of the force and the direction of the movement, the distance that the object is moved, is not the same. We're going to be calculating work in class, and I want you to make sure that you first determine whether or not work is being done by drawing a little picture of your force and distance arrows to determine whether work is being done. Because if work is not being done, there's no point in actually calculating something if there is no work being done. So the first thing you're going to need to do is determine if work is being done before you actually calculate then the amount of work done. All right, guys, your support item today is to find a ball, any ball. It could be a soccer ball, it could be a bouncy ball, it could be a tennis ball, it could be a basketball. You're going to take that ball, you're going to hold it out shoulder level, and you are going to drop it, and you are going to observe how that ball acts, and you are going to describe the motion of that ball in terms of a kinetic energy, potential energy transformation. In this case, your system is going to be open, there's going to be friction, there's going to be some thermal energy playing a role, and so I want you to describe, you can either use a bar chart to describe how the energy transformation is happening, or you can describe it in a few sentences. But don't forget your support item. That's all for me, guys. I'm out.